Can everybody see my screen now? Is my screen visible?
Yes, ma'am.
Okay, so this is the paper of that is, the formal name of the paper that we are doing, CC37 theory, and this is the revised syllabus. So we will start off the class with a question, all right? And this is the question: why quantum mechanics? Now, you have been doing classical mechanics since, I think, you have been doing classical mechanics for a long time now, right? In school, when physics started, you have been doing classical mechanics, although you did not know at that point of time that it was called classical mechanics and there is something else called quantum mechanics. But you did Newtonian mechanics in detail, and you all know what to do when you have a problem at hand, like a particle whose momentum is given at a point of time and whose initial and final velocities are known. You know how to see if it is accelerating. You know how to find out its path of motion by solving the differential equation that is given by Newton's second law. And you know that all bodies, all moving bodies that we see around us, including heavenly bodies, including, all the small and large vehicles, including the rockets that we send into space, the motion of everything can be understood by doing classical mechanics, right? So naturally the question comes, why do we need a different kind of mechanics when we can analyze the motion of all moving bodies around us using the Newtonian mechanics? Okay, so this is the first question that comes to our mind. In fact, I remember, I just, I like sharing my teaching experiences with my students. So when I started teaching, when I started off my career as a teacher, it was in, I started as a teacher at the Heritage Institute of Technology. I'm sure all of you have heard the name of Heritage Institute of Technology. And Heritage did not have a pure, the degree college back then. It was only the engineering college. And as my first assignment, I was asked to teach quantum mechanics to mechanical engineering students. Okay, so the engineering students, they have to study physics in the first 2 years. I think 2 semesters they have to do physics. So quantum mechanics comes in the second semester, quantum theory and then quantum mechanics. So I was asked to do this portion with the mechanical engineering students, all right? And you can understand it, that was the first year, my first year as a teacher. And I was just out of, not that I was really out of, university. I had finished university, then I had done my PhD and my postdoc, but I was never a teacher. I was never interacting with students. I was doing my own research work. So I really had no experience of how to deal with students, which I think I have a little bit now. So at that point of time, when I, started off with quantum mechanics, not really how I started off with you today, but these are the books that you should consult. And, I started right off from photoelectric effect, I think, if I remember, or I think black body radiation maybe. So after about 10 or 15 minutes of my class, which must have been very boring, I'm sure it was a very boring class, one of the students they were first year students, so they were there in class, but one of the students raised his hand and said, "Ma'am, I have a question." So I asked, "Yes, what is the question?" And he said, "Ma'am, why we are going to do mechanical engineering? Why do we need to study this? Why do we have to study quantum mechanics?" It was, his tone was like this. মানে ওর একেবারেই ভালো লাগছে না, আর মানে বুঝতেই পারছে না কিছু। আমারও পড়ানোটা নিশ্চয়ই খুব, আমি জানি না এখন আমি কেমন পড়াই, বাট সেই সময় নিশ্চয়ই পারতাম না কিছু বোঝাতে। তো and I had no answer really. আমি ওকে কিছুই উত্তর দিতে পারিনি, কারণ আমি খুব ঘাবড়েও গেছিলাম যে আমি এরকম প্রশ্ন তো আমরা কোনোদিন আমাদের টিচারদের করিনি, আমাকে এটা পড়তে হবে কেন? মানে আমি যদি জানি যে আমি জীবনে কোনোদিন হিস্ট্রি পড়বো না, তাহলে ক্লাস 9-এ আমাকে এত ইনভলভ হিস্ট্রি পড়তে হচ্ছে কেন? আমাদের তো এরকম কখনো প্রশ্ন করার কথা মাথায় আসেনি টিচারকে। Why do I have to study the history of how the French Revolution took place? I'm not going to study this in future. Okay, but he asked me that question, "Ma'am, we are going to do mechanical engineering. Why do I need to study this?" And my answer was, because it is part of the syllabus. Okay, so I just said that, I mean, this is part of your syllabus, you have to do this. And the number of students in my class started dwindling from the very second day, and I got a very, very bad appraisal in that semester. So I was very disheartened, and I went to the senior teacher of our department. I'm sorry, I'm taking up a lot of your time. Instead of going through the syllabus, I'm telling you all this blabbering of all this. Anyway, since I've started, let me finish. I hope you are not getting bored. Hello?
Absolutely.
Yeah.
Absolutely not, ma'am. Please continue.
Yes, so yeah, so I went to my senior teacher and said, "Sir, দেখুন এই এত খারাপ, মানে আমি জীবনে কোনোদিন কোনো স্কুলের বা কলেজের পরীক্ষায় আমি কোনোদিনও এরকম 65% পাইনি। আমি এরকম এত খারাপ পড়াই, আমি তাহলে কি করবো? আমার তো এই ক্যারিয়ারে হবে না, চলবে না। 67, আমি 67% পেয়েছিলাম পার্সেন্টাইলে, মানে অ্যাপ্রাইজাল, স্টুডেন্ট অ্যাপ্রাইজাল হতো হেরিটেজে, তো পার্সেন্টাইল ছিল 67%। যেখানে যে হাইয়েস্ট আর কি টিচার অ্যাপ্রাইজাল পেত, উনি হচ্ছেন আমাদের ডিপার্টমেন্টে যিনি হেড, মানে অ্যাক্রস অল দ্য ইঞ্জিনিয়ারিং ডিপার্টমেন্টস, all the core subject teachers, the head of the department of physics, he would always get 99% in student appraisal. মানে স্টুডেন্টরা নিজেদের কোর্স সাবজেক্টের টিচারের থেকেও এই স্যারকে বেশি দিতেন। হি ওয়াজ এ ভেরি নাইস পার্সন, আর ওনার লেখা সব বইও ইঞ্জিনিয়ারিং স্টুডেন্টরা পড়ে, ফিজিক্সের। So I went to him, and he's a very, very nice person, very good guide. In fact, I'm really indebted to him for changing my way of teaching, my mode of teaching. So I told him, so he said, anything happened? So I said, "Sir, একদম এরকম শুরুর ক্লাসে এরকম হয়েছিল, তো তারপরের থেকে তো ওরা খুব কম আসতো, আমার ক্লাসে কয়েকজন করে আসতো।" So he told me that, "You think yourself, why would a mechanical engineering student need to learn quantum mechanics?" And I told him, "Sir, I really don't know. Really, সত্যি তো কেন ওকে পড়তে হবে quantum mechanics? ও quantum mechanics পড়ে পড়বেটা কি?" This was my response, and he said, "তুমি এই কথা বলছো? তুমি একজন পোস্টডক্টরেট করে, পিএইচডি পোস্টডক্টরেট ফিজিক্সে করে এসে তুমি এই কথা বলছো?" Now basically my research was entirely theoretical. I have never done experimental research, but definitely I had some idea about. Then I said, "Sir, in the high energy physics experimental laboratories like CERN, I'm sure most of you have heard the name of CERN, like CERN and other such Fermilab and other such places where particle accelerators are constructed, who are the people who, the experiments are done by physicists, but who are the people who design these apparatus these large apparatus that run. If you are aware of it, the particle accelerator at CERN, it actually spans 3 countries: France, Switzerland, and which is the other country? Border ki thake bolo. Anyway, so it is across 3 countries, so you can understand how huge the thing is. Okay, so I said যে এই বড় যে অ্যাপারেটাস গুলো বিশাল সাইজের সব যে যেখানে হাই এনার্জি ফিজিক্স এক্সপেরিমেন্ট গুলো হয়, who are the people who construct this apparatus? They must be engineers, they must be mechanical engineers. And he said, of course, that is your answer. So if a person who is doing engineering is to follow a profession where at one point of time he is going to build up particle accelerators, he has to have an idea of basic quantum mechanics. Of course, a person who is going to be a computer scientist, at one point of time he will be doing only coding for multinational companies, or maybe even at a later point in his career he'll be making only Excel sheets. But if he is to be a really true computer scientist, he should know what parts are there inside the computer, how is the motherboard made, how are the integrated circuits made. He should know solid state physics, and solid state physics is based on quantum mechanics. If a person is doing civil engineering, he should know the basics of, if not quantum mechanics, but the basics of classical mechanics and general properties of matter and these things. So basic physics is a part of each and every technical scientific subject, and so there lied my answer. And I mean, this is just think of this as part of the story and not that something I'm boasting of. In the next semester, when I again got a new set of mechanical engineer student and a new set of computer science and IT students, when the way I started my teaching, the first class, it was not about the subject as it is in their syllabus, but more as to how they would benefit from learning physics later on in their career. And well, the picture was definitely different than what it was in the first year. So এতগুলো কথা যে বললাম আমি, মানে এত যে গল্প শোনালাম, তার কারণ একটাই, সেটা হচ্ছে যে this question: why quantum mechanics? Why do we need to start off from scratch with a totally new kind of mechanics when the mechanics that we already know has already given us answers about everything that we know and see around us? And the answer is that things on a very small scale, microscopic scale, things that we cannot see with our naked eyes, they behave like nothing that we experience in our daily lives. Okay, so yes, the fan that is running over our head, yes, the car that is moving on the road, yes, the aeroplane that is flying in the sky, the planet that we are residing on, or the star that we know about, the movement of these large bodies are explainable with the mechanics that we know till now. But things that are very, very small, even smaller than the specks of dust particles that we can see in the sunlight, even smaller than that. So you know what I'm talking about. I'm talking about things on the atomic scale, sub-microscopic, subatomic scale. They behave very, very differently. Okay? And this different behavior led physicists to customize this new kind of mechanics. All right. So a little bit of history. I will not tell you a lot of history because you will be doing this part in BM Sir's class. But I will just touch upon the facts that basically led to quantum mechanics. Okay. So we know that Newton said, when I did optics, physical optics with you in last semester, I told you a little bit of this in the first class, if you remember. So we know that Newton said light is a stream of particles called corpuscles, which gave us the corpuscular theory of light. But then there were experimental observations like, you know, the Young's double slit experiment, the diffraction, polarization, which demanded wave nature of light. Okay. So people like Huygens and Youngs and Fresnel and Fraunhofer and Malus and Brewster, all the things that we basically went through in our second semester module, they worked to establish the wave property of light. And you know that how at the almost simultaneously when optics, bunch of optics were forward with the wave property of light and the speed of this wave was being calculated experimentally, almost at the same time Maxwell summarized the electricity and magnetism equations into the four Maxwell equations, and he showed that this led to the differential equation, the solution of which was again a wave, the electromagnetic, and the theoretically calculated velocity of that wave matched the velocity of the experimentally calculated velocity of light wave, and they came to the conclusion that light is an electromagnetic wave in nature. Okay. Yes. So that's there. Now, all this, so this group of experiments and theories together sort of established that light was a form of wave. Remember that all this was pre-1900. All this was happening prior to 1900. Okay. Now, what happened post 1900? Post 1900, there came a drastic change in the points of view regarding light because of some new observations. Okay, so this again, this discussion not only shows us the reason for studying quantum mechanics or the reason for the establishment of quantum mechanics or quantum theory, but it also gives us a very important message that science is something that is never stagnant. Stop thinking differently, because you never know which observation will lead to something new. It is like this that several things have been discovered. If people did not think differently, if great scientists did not think differently, then such discoveries would not have been made. Okay. So if when the wave nature of light was established, after that observations were made which could not be explained using the wave nature. So if people with the wave nature, then the new physics would not be established at all. So my message is that, of course, go through the textbooks and read as we are teaching you or as you are understanding, but also never stop thinking differently. If you have a doubt about some observation, then keep thinking about it. Okay. So what happened post 1900? Post 1900, it was at this time that black body radiation was observed. Now we will study black body radiation in great detail in 5th semester. I will be doing, I hope I will continue teaching the same module then. So then if I teach the same module as I'm doing now, I will be doing black body radiation with you in great detail in the 5th semester. So for the time being, just remember that it was black body radiation was observed. Black body, you know, is something that absorbs all kinds of radiation that is incident on it, and then it radiates all kinds of radiation that was incident on it. So it has a very special feature and a very universal feature. But black body radiation could not be explained by the wave phenomenon. Wave nature of radiation could not explain black body radiation. So it was in 1900 and introduced the concept of quantization during energy exchange. In trying to explain, so there were several people who tried to explain black body radiation, but their explanations could not match the experimental curve. Okay, so Planck, while doing the same exercise, that is trying to explain mathematically, analytically, the experimental curve of black body radiation, he said that let me think that the energy that is exchanged between the radiation and the molecules that are forming the wall of the black body chamber, the box, okay, let me think that this exchange does not happen continuously but discretely. So usually we go from discrete to continuous, we change from summation to integration, but Planck went the other way around. You know, energy is a continuous entity. We know that there is no restriction on the maximum value of energy. It just depends on the amplitude of the wave, and it can increase indefinitely. But Planck said that no, let me think that this energy cannot be just any value. It has to be only certain discrete values. Okay, but he did this purely for mathematical purpose. He did this because he wanted to see whether taking this kind of discrete you know, entities, it would do him any help in doing the mathematics to analyze the graph of black body radiation, and it did, and so he introduced the quantization concept. Okay, then there was Compton effect. Again, this was something where you know, light is made to impinge on a certain target, much like X-rays, and the scattered light, when it is analyzed, it was seen that there was not just one wavelength, but along with the wavelength of the incident light, there was another wavelength, light of another wavelength present, which is lesser than the wavelength of the incident light. Again, this could not be explained using the wave nature of light, and Compton, this person Compton, used this discrete nature of light, and he could explain. He took light to be a stream of particles, but not just corpuscles according to Newton, but stream of certain particles which has a fixed energy, which has a fixed value of energy, and he could explain Compton effect. Then came photoelectric effect. Again, could not be explained using wave nature of light, and but when light was thought to be a stream of particles, this could be explained. So based on these experimental explanations by Planck and by Compton and by Einstein, Einstein proposed the existence of photons in 1905. Okay, he introduced the concept of photon in 1905. Before this, when Planck introduced the quantization of energy, Planck was a very rigid classical physicist. He did not believe in quantum physics. Okay, so he said that no. Light cannot be a stream of particles. Light is very much a wave. Only during the exchange of energy procedure, instead of exchanging energy continuously, it is exchanging energy as bundles. small bundles, each of a different value. So it is only the exchange process that this quantization is taking place, but otherwise light is a wave. Okay, so but Einstein for the first time said that it is not only during the exchange process, but in general, light that we consider as a wave can also be considered as a stream of particles called photons, each of which has a fixed value of energy given by h into nu, when nu is the frequency of the wave and h is Planck's constant. Now, Planck, as I told you, was a purely classical physicist, and he gave the value of h, again the calculation of which we will do when we do statistical mechanics in sem5. But the value of h, as you all know, is extremely small, of the order of, can someone tell me the value of h, Planck's constant? Can someone unmute and tell me the value of h?
6.624 in 10 to the power minus 34 joule per second.
10, yes, right, joule second, no, not joule per second, joule second, your first answer was correct. So 10 to the power minus 34, I want you to emphasize on this value, 10 to the power minus 34. So you can understand that, I mean, on a macroscopic scale, we would, for all practical purposes, neglect such a number, 10 to the power minus 34 joule second, the order, okay? And Planck was very happy with this value, because he knew that on the macroscopic scale, in a macroscopic world, this number has no importance because of its smallness, and classical physics would prevail uninterrupted. It would not be affected by the value of h. Okay? So Einstein for the first time gave the concept of photon in 1905 and depicted that light is also a stream of particles. Does that mean that the wave concept of light was wrong? No. It is under different circumstances that light behaves either as a wave or as a stream of particles. But under one set of circumstances, it will behave only as a wave or as a particle. It cannot behave both as a wave and a particle under the same set of circumstances. All right? But in general, we can now say that light is dual in nature. Light has dual characteristics. And it was later on we can, in fact, you can come to the conclusion from the different observations that when light interacts with light, like in interference or in diffraction, two waves interfering with each other, then the wave nature is what comes to the forefront. The wave nature is what plays the role, drives the engine. But when light interacts with matter, as in black body, as in Compton effect, as in photoelectric effect, it is then that the wave nature no longer can be the driving force behind the explanation. It is then that the particle nature of light comes to the fore. Okay? So light is something that we cannot strictly say is a wave, nor can we strictly say is a stream of particles. It is something that has dual nature, dual characteristics. Okay? So this is quantum theory, which you will be doing in detail in BM-SAR's class. If you think about the universe, there is either energy or there is matter. Okay? So universe is either made up of energy, which we think of as waves, or matter. We can see either material bodies or we can see energy. Not see, but I mean it's there. So universe is basically made up of energy and matter. Now we already discussed in our previous slide that energy is dual in nature, right? Energy is dual, electromagnetic waves, so they are dual in nature. So from the symmetry that exists in the universe, we have this intuition that matter must also be dual in nature. Since universe is a very symmetric space and time, and since it is made up of either energy, I mean it is made up of energy and matter, so whatever we see or feel around us, it's either energy or matter. Now if energy has dual characteristics, then to maintain balance, to maintain symmetry, there was this intuition that matter must also be dual in nature. Okay, and in 1924, so in 1905, Einstein gives the proposal of the existence of photons, the particle nature of light, and 20 years later, in 1924, the French person, this actual prince, he was a prince, and in fact this person, Louis de Broglie, he was a medical student, and he was visiting his brother who was a physics student. So he was doing some experiments, his brother, I don't remember the name of his brother, and when Louis de Broglie visited his brother where he was, the laboratory where he was doing the experiments, he went through the papers. He went through some papers by Planck and also by Born, etc. And not Born. I don't remember the person Louis de Broglie's brother was working with. I'll find it out and tell you. I'm not remembering the name right now. I think with Planck only. I think he was working with Planck. Anyway, so Louis de Broglie went through some papers and he started studying. He became interested in this part of physics, and he started going through more such papers, and he sort of as a hypothesis, purely as a hypothesis, no experimental basis right now, but as a hypothesis, he said that it is not only that light, which under certain circumstances shows characteristics of particle, but all moving objects in the universe have associated with them a wave, the wavelength of which is given by lambda equal to h by p, where p is the linear momentum. Okay, so this was a pure hypothesis by Prince Louis de Broglie. The pronunciation is not Broglie, although we have a tendency to say de Broglie waves and de Broglie particles, but please, de Broglie wavelength, please know this, that the pronunciation is Broglie, okay, Louis de Broglie. The S is silent and the G is silent. So Louis de Broglie gave this hypothesis on, I would say, rather ad hoc basis, that just like light has dual character, under certain circumstances it behaves like a wave, under different circumstances it behaves as a stream of particles called photons. Okay, he said that any moving object, the tennis ball, the planets, the bus, you, me, everyone, when we are moving, when the object is moving, it has associated with it a wave, and the wavelength of that wave is given by lambda equal to h by 2. Okay, so as I told you, this was a hypothesis, obviously waiting for experimental verification. All right, and just 2 years after this experiment was done, and in 1927 Davison and Germer published their paper on the Davison-Germer's experiment, where they saw diffraction-like intensity pattern for electrons. You all know what a diffraction pattern looks like, diffraction fringes, how they look. We have done it in detail in our optics class in the previous semester. Davison and Germer observed that when they made streams of electrons incident on a crystal, okay, not just any object, but if electrons are made incident on a crystalline structure, some solids, some crystal body, the observation was that diffraction pattern was seen, not on the screen, but on the intensity detector. The detector showed how will you detect electrons? By current, because when electrons move, there is a current associated with it. So the intensity of this current showed the characteristics of the diffraction pattern intensity. So this experiment sort of established the fact that under certain circumstances, electrons behaved as waves, not particles. Okay. Then, almost at the same time, Laue pattern was observed for neutrons. Neutrons, again, you know, are subatomic particles. When neutrons were diffracted through certain crystals, it was seen that, Laue pattern is something that is observed in X-ray. When you make X radiation incident on some crystals, you can see an intensity pattern which is known as Laue pattern, after the first person who observed this pattern. Laue was the name of that person. So using neutrons also, this kind of Laue pattern was seen. So again, establishing the wave nature. Laue pattern was also observed for hydrogen and helium atom diffraction. When hydrogen atoms or helium atoms were made to diffract from X-ray, from certain crystalline structures, again Laue pattern was observed. So these experiments showed that it is not only that light that has dual character, but matter too has dual character. Particles like electron, like neutron, like hydrogen and helium atoms, which we know that they are particles, they are matter. But under certain circumstances, it was seen that they exhibit wave nature. They undergo phenomena, the observation of which can be explained only if you take their wave nature into consideration. Okay, so de Broglie's hypothesis was proved experimentally a few years after he proposed the hypothesis, and the dual character of matter was also established. So it is not only that light has dual character, matter too has dual character. So now we have coined the term wave particle duality to everything in the universe. Every object, I shouldn't say object, everything in the universe, be it energy, be it matter, everything is dual in nature. Okay, of course, both the characters cannot be observed simultaneously. Under different circumstances, different characters are exhibited. So there, now obviously for light, the wave nature was first established and then the particle nature was figured out. For matter, we are familiar with the material nature, the particle nature, and so began the quest for the matter wave. People started to do experiments, do calculations in search of this matter wave. What is the nature of this matter wave? Is it an electromagnetic wave the same as light wave? Okay, thus began the quest. Now, Niels Bohr, all of you have heard of Niels Bohr, the Bohr model of atom. So Niels Bohr gave the principle of complementarity, which said that wave and particle models are complementary to each other. Okay, so this was the principle of complementarity, that waves and particles, wave nature and particle nature of energy and matter are complementary to each other. So we cannot say that radiation and matter are simply waves or simply particles. A more general model is required. We need a more general model which will encompass the dual nature, so that under special circumstances we will get the wave nature, and under a different set of circumstances we will get the particle nature. And this could be done only by the probability interpretation. This was done by formulating the probability interpretation. As you can understand, that it is a probabilistic phenomenon. It can either behave as a wave or it can behave as matter. We cannot tag anything that this is matter, this is wave. No, we can't do that. It can show either wave nature or particle nature, and for that we have to switch over to a probabilistic interpretation. Okay, now this probabilistic interpretation was given by Einstein for the particle nature of waves, and it was given by Max Born for the wave nature of particles. Einstein used this probabilistic interpretation to firmly establish the particle nature of waves, whereas Max Born used the same probabilistic interpretation to establish the wave nature of particles. Okay, so how did Einstein do this? He did this by using a statistical treatment of radiation. Okay, now right now we are not going to do this, but as I told you, this is the statistical treatment of radiation. It's going to be a part of statistical mechanics, and we will be doing that in the 5th sem. I think partly it will be done by BN sir in his quantum theory class, but in more detail, in a statistical point of view, we will be doing it in a 5th sem. But for now, just remember that Einstein used statistical treatment of radiation. Whereas, so in this treatment, what was done is the exact number of photons, that is replaced by the average number. All of you know, even if you don't know any statistics, you know that in statistics the main criteria is mean, MEAN, mean or average. Okay, so what Einstein did was, instead of taking the exact number of photons that pass a given that cross a certain unit area of cross section, he used the average value. So Max Born used a similar statistical model for matter, and he incorporated this into the function which will represent the de Broglie wave. So de Broglie only gave a hypothesis which said that this is the wavelength of the wave that might be associated with a moving particle. But that, that was just the value of lambda. That does not show you what is the nature of the wave associated. To know that, to understand what matter wave really is, Max Born used the statistical interpretation, and that he incorporated into a certain function that will represent the de Broglie wave, for which the wavelength value was given by de Broglie. Okay. So this wave is associated, this wave that of course is, associated with a moving particle. Just let us for the time being associate it with the normal wave function that we know. Psi of xt equal to a sine 2 pi x by lambda minus vt. Okay. Now you can see that this is analogous with the expression of electric field. We know that a sinusoidal electromagnetic field with a certain wavelength lambda is given by a sine 2 pi x by lambda minus vt. So you can see that these two expressions are very similar in nature, but this is an electromagnetic wave and this is the supposedly existing wave that is associated with a moving particle. I am still using the word supposedly. Now for this wave, we know that the intensity is given by the amplitude square. So the intensity of radiation in classical treatment is given by this mod E square, and it is proportional to h nu n, where nu is the average number of photons and h nu is the energy of each photon. So it must be that the total energy should be the the value should be given by the total number of photons multiplied by the average number of photons multiplied by the energy of each photon. Similarly, mod psi square should be playing a similar role in case of matter waves, since the look of the equation is similar and since we are saying that they are complementary to each other. Therefore, Max Born sort of made this assumption that the role of mod psi square in case of matter waves should be the same as that of mod E square in case of electromagnetic waves. And so from this we have the Born interpretation that gives the probability of finding a particle within a given interval in space at a given time. Okay, so this is something very, very important. This is something that you will not Google out if the question is given in the examination. I have given this question for examination in previous semester and I have got answers which are extremely, what should I say? Trash is the only word that is coming to my mind, and I don't know from where the students get those answers. Definitely not from any book. I don't know from where. When I ask for Born interpretation, please say that it gives the probability of finding a particle within a given interval in space at that time. Born interpretation gives us just that probability, that if you are trying to track a particle, what is the probability that it will be present within a certain interval of space at that point of time? Because the particle is next, it is moving. So if you are trying to, track it down, what is the probability that at a certain instant of time you will find it at a certain range? This is the formal statement of Born interpretation. I will not read it out, but you must go through it. The idea is very simple. Suppose a particle is moving with a certain velocity. So you want to know that say after 5 minutes of starting your observation, where can you find the particle? All right. So you place cameras. This is a hypothetical experiment, a thought experiment. You place cameras all along the path of the particle, and the cameras continuously take pictures of the particle. So at that instant of time where you want to know the position of the particle, And then you take out the pictures and you see that the camera placed at a certain space has taken the maximum number of pictures at that point of time of the particle with the particle present. So you know that the probability of finding the particle at that point is highest. All right. This is exactly the idea of Born interpretation. This is how the probability concept is introduced. That the modular square of the wave function is nothing but the probability of finding the particle within a certain interval of time within a certain interval of space at certain instant. So it will be high at a certain point and low at other points. So the probability of finding the particle at the high value is highest, and at the low values it becomes small, that it is less, you are less probable to find. For example, I'll tell you, suppose you go to college on a under normal circumstances, and you ask somebody, where can I find KH, ma'am? Okay, you ask somebody in the office, where can I find KH, ma'am? So he will tell you automatically that in physics department. Now this answer, when he tells you that you will find KH, ma'am, in the physics department, does it ensure that with 100% chance you will find me in the physics department? No. Because I might go to the library, I might go to the washroom, I might come down to the canteen, I might be in some class, I might go out to have a cup of tea, right? So it does not ensure that you will find me in the physics department with 100% chance. But since I belong to the physics department, therefore the most likely place where you can find me is the physics department, right? Now, for example, I have a class in room number 603 at 11:30 a.m. Okay. So now suppose you ask somebody, where can I find KH, ma'am? Chances are, suppose you ask somebody from the department, from the physics department, that where can I find KH, ma'am? So from the office you come up to the physics department and you see that I am not there. Okay. So then you ask somebody from the department, where can I find KH, ma'am? What will he or she do? He will look at the routine and say that, oh, now she has a class in room 603, so you'll find her there. So again, it is most likely that you will find me in room number 603, because at that point of time I have a class in room number 603. But again, you can't be 100% sure. You can be, say, about 95% sure, because while taking the class, maybe I have had a phone call which was emergency and I had to attend to. I might, for some reason, maybe the principal has called me for some reason for a discussion at that point of time, and I may have dismissed the class and gone to the principal's office. Okay. So these are all chances. But if you draw a graph of the position at which you will find me, the highest will be at any point of time, the highest chance will be in the physics department. And if you go by the routine, then say at 11:30 a.m. on Monday, the highest chance will be in room number 603, where I have a class at that point of time. Have I been able to make you give you an idea of, have I been able to give you an idea of what I mean by this probabilistic approach? খানিকটা অন্তত কি বোঝাতে পেরেছি? Okay, so this is Born interpretation. This is what we will come across mod chi square several times now. This is the interpretation of mod chi square. Just like mod E squared in electromagnetic wave gives us the intensity. Okay, similarly mod chi square gives us the probability of finding the particle at a certain interval of space at a certain point of time. Okay. So there was this major switch over in quantum mechanics. From deterministic, we switch over to probabilistic. And there comes Heisenberg's uncertainty principle. Once again, part of your quantum theory syllabus, so I will just mention. What does it say? It says that simultaneous measurement of position and momentum cannot give results more accurate than by given by this relation. So when you are trying to measure position and momentum of a particle simultaneously, you cannot be more accurate than that given by this result. The product of the range of x and the range of px, delta x and delta px, must be greater than equal to h cut by 2. We will discuss this in some more detail later on. For the time being, just know that even with the most accurate apparatus, there will be some error in the measurement of x and there will be some error in the measurement of px if you're trying to measure them simultaneously. That is Heisenberg's uncertainty principle. So uncertainty now becomes a part and parcel of life in quantum mechanics. You cannot say anything with 100% surety. There will be a little bit of uncertainty, and that will be governed by Heisenberg's uncertainty principle, HUP. You cannot pinpoint on anything at a single point of time. There will be a range always. Okay. So the wave function representing a free particle, if you want to write down the wave function representing a free particle, you have to consider a particle of mass m and momentum px, which is moving freely. No forces acting on it. It is moving freely. And of course, we are considering non-relativistic motion. Okay. So if you are trying to talk about a free particle, and if it has a definite momentum, if you are definitely saying that it has a momentum, say 50, what is the unit of momentum? Mass into velocity. Kg meter per second. 50 kg meter per second is the momentum, which means that you are fixing the value of momentum, so there is no uncertainty in momentum. Delta px is 0. The moment delta px is 0, if you check this Heisenberg's uncertainty principle, which I am claiming is true for all particles in following quantum mechanics, then since delta px is 0, what is the value of delta x? If delta px is 0, what will be the value of delta x?
Undefined.
Undefined. Infinite. Infinite. The range of delta x becomes infinite. So the position of the particle becomes completely undetermined. The particle can exist anywhere along the entire x-axis for 1D motion. So if you fix the momentum, you cannot have any idea about the position. From de Broglie's hypothesis, since lambda is equal to h by px and nu is equal to E by h, nu means frequency is equal to E by h from Planck's hypothesis, we introduce some new parameters where h cut is h by 2 pi and wave number k is 2 pi by lambda. So we can write px, which is h by lambda, equal to h by 2 pi into 2 pi by lambda. So px can be written as h cut k and E can be written as h nu. So h by 2 pi into 2 pi nu. So E can be written as h cut nu. Okay. So you know that nu and lambda, wavelength and frequency, are wave parameters. using the wave parameters in de Broglie's hypothesis and Planck's hypothesis, we introduce new parameters px and e, which are particle parameters. Okay, so expression of p and e, momentum and energy, in terms of lambda and omega gives the particle parameters in terms of wave parameters. And momentum being specified, which means the position can be anywhere along the x-axis, we can represent the free particle by a plane progressive wave, a monochromatic wave, because we know that the extent of a monochromatic wave is infinite. It can extend from minus infinity to plus infinity. So the wave function will be like this: a e to the power minus I omega t minus kx. Instead of a sine or a cosine function, we are using the complex nature. Okay, or a e to the power. So now instead of omega and k, the wave parameters, we replace them by the particle parameters. A e to the power I by h cut pxx minus et, using expressions of p and e. So this is a complex function, and interpretation of how such a complex function might represent a real physical particle comes from the probabilistic point of view of quantum mechanics. So for a free particle, if we want to show what kind of a wave will represent a free particle, then we can see here that since a free particle has a fixed momentum, therefore its position is totally undetermined, and therefore the only kind of wave that can represent a free particle is a monochromatic wave. And we write the monochromatic wave in terms of the particle parameters by using the relation of the particle parameters with the wave parameters, and we get the complex function. Okay, now particle is very much real in nature, so how can a complex function represent a real particle? That comes from the probabilistic interpretation. Okay, so for any direction, for movement in three-dimensional, we just, instead of x, we use the vector r, and this is the expression of the monochromatic wave that is associated with the moving free particle. Okay, we'll end our class today. I gave you some very new concepts, totally new ideas. So I will of course recapitulate all this in the next class, at least the portion from where we started off with quantum mechanics, not the earlier part, but from where the probabilistic ideas started over here. I will of course recapitulate that, but it is my ardent request to you to please go through the slides before the next class and see how much you have understood and how much I need to re-explain. Without your cooperation, it is not possible for me to continue. You need to go through the slides and see exactly where you need re-explanation and tell me in the next class, ma'am, please explain these portions again. And I will specifically repeat those portions, because a very fair idea, a clear idea. I'm not saying that you will learn quantum mechanics in a jiffy. It is not a very easy subject, and it is a very abstract subject too. But for a fair idea, for a clear concept of the basics, you need to ask questions. You need to read yourself to see how much you have understood and how much you have not. Okay, so for that you have to cooperate with me. Clear?